Welcome to the U.S. Department of Energy's Argonne National Laboratory. I'm Roger Blomquist, and I'm going to take you on a tour of Argonne's Nuclear Energy Exhibition Hall, which shows a lot of history about Argonne, and also current work in our efforts to advance nuclear power and nuclear technology in general for the betterment of mankind. But first, let's start with the history. So this is a model of Chicago Pile 1, which is the first reactor or the first self-sustaining man-made neutron chain reaction in human history. And this was part of the Manhattan Project. On December 2nd, 1942, this system was taken critical. And critical is one of those unfortunate nuclear engineering terms which sounds really bad, but it means the chain reaction is continuing very smoothly and stably and constantly. And so when a reactor is critical, that's its state that you want it to be in for if you're producing power making money or if you're doing experiments for irradiating materials. Anyway, this was part of the, as I mentioned, this is part of the Manhattan Project, and the idea was to prove that we could produce and control a neutron chain reaction in a reactor. Now, my definition of a chain reaction is a reaction in which one of the products is also one of the inputs. So, for example, money, or the economy, is a chain reaction where money is one of the outputs and one of the inputs. In the same way, a nuclear reactor has got a neutron chain reaction where neutrons are produced in fission when the uranium atoms are split. They also cause the fission, so it's a circle just like like money in the economy. Anyway, this was a pile of graphite blocks, about 21 feet tall, 21 feet in diameter, and roughly a spherical shape. And there were several dozen scientists and engineers present on that day. The pile of graphite blocks had some of them with large holes bored in them and uranium slugs put in those holes. And the uranium is where the fissioning occurs, where the chain reaction occurs. The graphite was necessary to slow down the neutrons because slower neutrons are better at causing fission in uranium than fast neutrons are. And neutrons come out of fission very fast. So the graphite slowed them down to make the chain reaction possible. So you can see there's some scaffolding there that has one of the control rods. That's an emergency rod. It's held out with a rope. And there's a control rod that's operated by the man in the white lab coat. He is the control rod drive mechanism. Fermi would tell him to put the rod in or pull the rod out so many centimeters, and he would actually put his hand on the rod and move it. Now this whole experiment was conducted it was top secret, of course. This is the Manhattan Project after all. The ultimate object was to produce nuclear weapons because we were afraid the Germans, who were very good at science and engineering, would do that first, and we knew that if they did, they would not hesitate to use them. Anyway, it was a top secret project. It was performed at the University of Chicago under the football stands at Stagg Field and in a squash court, or excuse me, a racquetball court. A racquetball court is particularly handy for this because it has no windows. So from a security point of view, all you have to do is control who comes and goes and what they say to others once they're outside of the experiment area. So this is why it was done in a racquetball court. So on that day, they operated this, they took this reactor almost to critical, and it was about noon. So Enrico Fermi, the technical leader for this, said, "Okay, shut it down, let's go to lunch." He's Italian after all, from Italy, and so nobody ever missed a nice long lunch. And so they all went to lunch and came back that afternoon and then finished pulling the control rods out the rest of the way and produced a self-sustained chain reaction. After about 20 or 30 minutes, they shut this system down and they celebrated with a bottle of Chianti with little communion cups, and everyone toasted their success. This was equivalent to inventing fire, It's a new form of energy that could be released. It was demonstrated. And then after work, they all went home that day and they couldn't tell a soul because it was top secret. So I can now show you what the fuel looks like in there just for a hot minute. And so you'll understand better how this pile of graphite blocks was put together. So this is what the fuel in Chicago Pile 1 looked like. Now, this actually is Chicago Pile 1 graphite. Graphite does not get radioactive in a reactor, so it's perfectly safe for me and the cameraman here. But I want to point out the holes drilled in the graphite here, each of which has a uranium slug in it. And this is done in every second layer of these, and they're about 8 inches apart. So this whole reactor, from a graphite slug point of view, looks like a three-dimensional square array of these uranium slugs immersed in graphite. And the neutrons are born in the fuel, in the uranium. They fly out into the graphite, are slowed down, and they drift back into the uranium to cause the chain reaction. So let's now take another step in history to Argonne's early history and the beginnings of our reactor development projects. This apple tree represents Argonne's early nuclear history and points to the future direction of our research and development in nuclear energy. Each apple is a reactor or a critical assembly facility that was designed by Argonne. The red ones were designed, built, and operated at Argonne, by Argonne, and the green ones were built somewhere else, and there were 2 that were canceled. We begin with Chicago Pile 1, which was not really an Argonne reactor, but the same people who built Chicago Pile 1 were the reactor people that founded Argonne National Laboratory, which was established officially in 1946 after World War II. So there are 4 main branches in this tree. This is pressurized water reactors. This is research reactors. This is boiling water reactors. And this is fast neutron reactors. And I'll spend just a minute on each of those. You can explore this to your heart's content at our website. And there is pop-up information for most of these that you can learn more about each of these. And there's a very nice Lego movie about the Chicago Pile 1 experiment too. So pressurized water reactors began with the US Navy. Hyman Rickover concluded that submarine propulsion would be very nice if it didn't require air to burn fuel. And so he saw nuclear power as a way to propel submarines in a way that would give them high speed and submerged endurance. Argonne worked with the Navy and with Westinghouse Electric and designed the first core for the USS Nautilus. Westinghouse then designed and built the balance of plant, and they then took that technology and commercialized it, and that's where we get today's commercial pressurized water reactors from. In the United States, that's about 65% of our commercial nuclear power. These are research reactors of various kinds. I won't go into a lot of detail, but they include heavy water reactors. And Chicago Pile 3 was a heavy water reactor, and we worked with Canadians on that. And the Canadians then took that technology and commercialized it as the CANDU reactors, which is also one of the more common commercial electricity generating reactors in the world. Argonne invented the boiling water reactors, which is a bit like a pressurized water reactor, only in some ways simpler. And we ran a series of experiments at Argonne West in Idaho that proved that the neutron chain reaction was stable in the presence of boiling. And you want stability, you don't want instability. And then the fast neutron reactors is really Argonne's signature achievement, and also the direction in the future that nuclear power will take. And it began in 1951 with experimental breeder reactor number 1, which is the first fast neutron reactor to produce power and also to breed fissionable materials. And these other zero power reactors are critical experiments. By that, I mean a the power is so low, it's not zero, but it's very low, low enough that it doesn't require a cooling system. And that makes an experiment far, far cheaper and also safer to perform. So they're much easier physics experiments. And we use these to evaluate how materials behave in the reactor core from a nuclear standpoint. So now let's move on to the commercialized pressurized water reactor. So this is a model of a pressurized water reactor fuel bundle. From a small reactor, actually, it's only 150 megawatts. That reactor is now shut down because it was really too small. But this gives you an idea what a reactor fuel bundle looks like. A reactor core is a rack of these things about 12 feet in diameter and about 12 feet tall. So it's pretty big, but that produces 1,000 megawatts, which is a lot of electricity. So for example, in the state of Illinois, we get about half of our electricity from nuclear, and that's typically about 11,000 megawatts is nuclear. So that gives you an idea of how much space these take up. It's not very much, even though they're individually large. But anyway, the way this works is these are hollow metal tubes, and inside these tubes are stacks of uranium dioxide fuel. It's enriched uranium, not highly enriched, but low enriched uranium, and that's where the chain reaction occurs. And in between these pins, or rods, is water. Water is a cooling medium, and it slows down the neutrons in the same way that the graphite slows down the neutrons in Chicago Pile 1 that we discussed a minute ago. So the way this works is water gets pumped in, flows down the outside of the reactor, and then up along these pins and sucks the heat out of the pins. The pins have the hot uranium dioxide inside, and basically they're sucking the heat out, and then that hotter water goes out the top and then goes on to produce electricity. And I'll show you in a minute on this poster how that works. So this rack of fuel bundles here. The water gets pumped in, flows down the sides and goes up along the fuel rods, gets hot, and then goes to what we call a steam generator, it's a heat exchanger, just like your car radiator. In your car radiator, you've got engine coolant inside and air on the outside. In this case, we have the radioactive reactor coolant on the inside, and then on the outside we have also very high temperature water that boils to steam and flows to the turbine. It spins the turbine like a windmill, and that turns a generator to produce electricity. And then there's waste heat that comes out of this. From every process like this has some inefficiency, and the waste heat is ejected in this cartoon in a cooling tower. But you can use the ocean, which is what we did on my ship. We were surrounded by our heat sink, which is very convenient. But these are the iconic cooling towers that you normally see with a nuclear power plant. So that's how this fits into a power plant. And it turns out, per amount of energy produced, it's very compact. And that's because uranium has 1 million times the energy density of, let's say, natural gas or coal. It's a fabulous fuel in terms of the amount of stuff you have to dig up and use. That's what makes it environmentally benign. So now let me show you how the control rods, they fit inside of this, and I'll show you that in a minute. And I'll also show you a picture of the cooling towers, which I'm sure you've all seen. So here's a photograph of a nuclear power plant in Illinois, and these are the reactor buildings, and these are the cooling towers. A lot of people imagine these are the cooling towers, and of course, if that's what you're thinking, the first thought that comes to mind is, my gosh, look at all that pollution coming out. In fact, this is just water vapor that goes into the natural hydrologic cycle. So when you see these cooling towers, it may not be a nuclear power plant. These are used in some other kinds of power plants as well. Now, as to the control rods, this is actually a wooden reconstruction of a Westinghouse reactor control assembly, and these are individual control rods and they go into locations inside of this fuel bundle, which is a lot like the one I just showed you, that has some empty positions that these can go into and come out of. So that's how the chain reaction is controlled. These contain materials that absorb neutrons, and that's when you put them in, that's what chokes off the chain reaction and shuts down the reactor. So now, keep in mind how big and bulky this and the model I just showed you are, and now let's look at the fast reactor equivalent. So this is a model of one of the first fast neutron reactors, the first one that produced power. It's one of the ones on the Argonne apple tree I showed you. And it's EBR1, experimental breeder reactor number 1, except in this model we have removed much of the stuff outside of the core, the reflectors, some of the blankets. So here is the reactor core itself. In here, these larger rods are blanket rods where uranium-238 absorbs neutrons and eventually turns into plutonium-239, which is a very nice reactor fuel, just like uranium-235 is. And then outside is a reflector and additional blankets for making additional fissionable material. These are the control rods, so notice they are not inside the core. They're outside the core, and that works because this core is so small, a large fraction of the neutrons leak out into this area out here, and many of them would leak back into the core, except for when these control rods are in, they absorb those neutrons and shut down the chain reaction. So the interesting thing about this reactor is this is pretty small. It produced about 1.5 megawatts of power, which is a lot of power for this small volume. And the most important thing is this reactor produced electricity in 1951. That is only 9 years after the Chicago Pile 1 experiment, which first demonstrated the neutron chain reaction. So 9 years from a physics experiment to an operating test, demonstration test at sort of at lab scale is a remarkable pace of innovation. This reactor, Argonne designed, built, and operated for 30 years at Argonne West in Idaho. And you'll notice it looks a little bit different from the big one I just showed you that was one from a modern commercial pressurized water reactor. Here the fuel pins are only this long, and they're much smaller. Now this is only a 20 megawatt reactor instead of a 1,000 megawatt reactor. But if I were to expand this to be 1,000 megawatts, it would be about 1 meter tall and about 1 meter across, roughly. So it's way more compact than our current commercial reactors. And how do we do that? Well, we don't use water to cool this reactor. We use liquid metal sodium, which is 100 times better at sucking the heat out of these fuel pins than water is at sucking the heat out of fuel pins in a water-cooled reactor. And that means we need a lot less coolant, so we can pack the fuel pins much more tightly together and have a much smaller reactor. There's another tremendous advantage to using liquid metal sodium or molten salt, for example, to cool an advanced reactor, and that is when you heat it up, it doesn't go to high pressure. So those of you who have pressure cookers, you know when you put the pressure cooker on the stove and heat up the water inside, it doesn't boil, it just builds up the pressure inside. So you need a very heavy pot for that. In this case, when you heat up the sodium to reactor temperatures, which are very high, then the pressure doesn't go up. So you need a low pressure system, much thinner vessel walls compared to a commercial pressurized water reactor, which needs a reactor vessel of about 8, 9, or 10 inches thick to contain that pressure. You can imagine that would be rather expensive. It's also tricky to weld, uses a lot of material, and it just adds to the expense and complexity of the system. But I'll go into a bit more detail on this as we now look at the model of the reactor that this was in, experimental breeder reactor number 2. So let's go there. So this is a model of EBR2, experimental breeder reactor number 2, which Argonne built and operated at Argonne West in Idaho. It was constructed in 1964 and it operated until 1994. It was a full power plant in terms of capability. It only produced 20 megawatts electric because it was a demonstration project, not a commercial project. So I just showed you the fuel elements. So each one of these red elements here is one of those reactor fuel elements shown here in the center of the reactor here. And as I mentioned, this is a low pressure system, so we can afford to make a very large reactor vessel. So here you can see around the outside is a reactor vessel which contains the sodium. And it's sort of like an inch, inch and a quarter, inch and a half thick, which is way cheaper than this big pressure vessel that our current commercial reactors use. In fact, at EBR2, we put a second one outside of the inner one in case the inner one leaked. We still had the sodium contained. Now, notice the core takes up a very small percentage of the volume of this reactor vessel. In a modern water-cooled commercial reactor, that vessel is so expensive that we kind of have to shrink wrap it around the reactor vessel, around the core. And that means there isn't a lot of excess coolant in there if we lose the ability to cool a reactor. And that was one of the issues that confronted the Fukushima workers when they lost offsite power and the ability to cool a reactor. In this case, this whole thing is pretty much full of sodium, so there's like weeks worth of cooling in here if we lose the ability to pump the sodium around. And in fact, the sodium in the core heats up and naturally flows due to natural circulation, just like your fireplace chimney works at home with no pumps or blowers or fans or anything like that. So this reactor is what we call inherently safe. And we demonstrated that at this reactor in Idaho. We ran a series of tests. We took the reactor to 100% power, and then we shut down the safety systems that would tell the control rods to go in and turn off the chain reaction. And then the reactor operators turned off the reactor cooling pumps. So that was effectively like trying to sabotage the reactor. Now, we'd analyzed this ahead of time. We knew what we were doing. We knew it would end nicely, and indeed it did. So what happens is when the sodium coming through the core slows down, because remember, we just turned off the pumps, it heats up more, and the core expands a little bit, and more neutrons leak out, and the chain reaction shuts down. And it just sits there and simmers for weeks at a time. Now, at Fukushima, the operators had about 45 minutes after the tsunami hit to get some cooling going. That's not nearly enough time. Remember, they were in the middle of a disaster. Both the earthquake and the tsunami destroyed their backup power system and much of the other stuff at the reactor site that they could have employed in that. So in that sense, this reactor is inherently safe. So I should say the other advantage for this kind of reactor is as I mentioned before, we're not slowing down the neutrons because sodium does not slow down neutrons that come out of fission. And at high neutron energy, the kinds of nuclear reactions that occur are rather different than they are at low neutron energy. And this makes this kind of reactor easy to configure as a nuclear garbage disposal. So we can take used fuel from other reactors and recycle it into this reactor and destroy it, so that the amount of waste, the period of toxicity of the waste goes from several 100,000 years down to a few hundred years. And I would argue that a good engineering program could find a way to safely store something for a few hundred years. After all, the cathedral in Paris was 1,000 years old. And even when they had this horrible fire a few years back, the whole building didn't collapse. It was the roof that burned. So I think that is one tractable solution for what is considered the nuclear waste issue. So let's move on. We'll spend a minute or two on fuel recycling that was associated with this, and then maybe a little bit about nuclear chemistry. So let's step over to the recycle facility that was attached to this reactor. So attached to EBR2, which I just showed you, is the fuel cycle facility. And this facility's purpose was to take used fuel out of EBR2 and recycle it and put it back in. So this is it's called closing the fuel cycle, and it means that you have a lot of control over what constitutes the ultimate nuclear waste. And I will give you a tour of all these stations in a minute using a poster, but if we look over here, you can see these master-slave manipulators, which are used in hot cells. This is really a big hot cell. It's got 4-foot thick concrete walls for shielding because the material inside of this is highly radioactive. So the fuel will come in through a tunnel up into this section here and have the ends cut off, so we only have the rods. And then the rods go through a little porthole into this facility, and then there's a series of stations that go around here, and so the fuel is recycled, and then the fuel elements are basically reconstructed with new materials, new structural materials, and then taken out and put back in the reactor. And we had done this at Argonne West many, many times. So it's been thoroughly demonstrated, lots of the kinks worked out, and so forth. So let's turn our attention to the diagram so you can see how it works. Here we go. We're coming in through the tunnel up into this room. It's called an air cell because it has regular air in it, but it's got some radioactive material in it, highly radioactive. So you see here the thick concrete walls and the windows filled with a radiation absorbing material. You can still see through it, but the radiation doesn't make it through the windows. And here, this is the room where we cut off the ends, the hardware, and then we slide through this little port here, the fuel rods that go into the facility where the real work occurs. And here, the fuel pins get chopped into little pieces. They get put into an electrorefiner, which is an electrochemical process, a bit like battery charge and discharge that somewhat separates the materials. And the product from that gets melted and then put into molds to make new fuel pins. And then these are assembled and then brought out, and then the final work is done in the air cell and it goes back into the reactor. So that's how this works. No people can go in here or in here because it's highly radioactive. So equipment that's in here, if it breaks, you have to have a way to fix it. And there is a station we can bring this stuff to where people can work on it. But this is much simpler than the recycling system that the French use. They use a system called Purex for plutonium extraction, plutonium-uranium extraction. And it uses water chemistry, which requires miles and miles and miles of piping containing corrosive nitric acid, that contains all these nasty fuel materials, and it's much more expensive than this process. It also separates the plutonium, which is something we don't want to do, and this system doesn't really do. So the material that comes out of this, that goes back into the reactor, the reconstituted fuel elements, are still highly radioactive, so no one can steal them. They would die in the process, and it's the wrong material to use for any sort of a nefarious purpose like an illicit weapon or anything like that. So that's how this system works and how it fits together with EBR2. And we envision that we in this country and other places around the world, will build sites with sets of EBR2 type reactors with attached recycling facilities. So there's no shipping this fuel back and forth. You just load up the reactor at the beginning of its life, and then you run it for its whole life without shipping any fuel. So one of these facilities, if it were a little bigger, could service, I don't know, a half a dozen or more of EBR2 type reactors that are producing more than 20 megawatts, obviously. So let's move on, and I'll show you a little bit about how toxic materials are handled in laboratories here at Argonne and at other facilities too. So here's a model of a glove box which is used to perform operations on toxic materials. And that includes mildly radioactive materials, but not intensely radioactive materials. The whole idea here is to keep toxic dust, fumes, and whatnot inside this and away so that humans cannot ingest it. So it's not radiation shielding per se. And the way this works is there are these glove ports, and you can stick one or both hands into gloves, and then you can perform manipulations with all the tools in here, do your experiments and whatnot. And one of the things I want to show you here is what the fuel element segments look like once they're chopped up in the facility that I just showed you. They're fairly short, and you can see they're pretty small. And they go into this fuel dissolution basket right here, which sits in a molten salt bath, and that's where the actual materials get sorted out. This molten salt bath is kept at about 300 degrees centigrade, so it's very, very hot. But it's low pressure, so it's not that much of a complication. So now I'd like to switch gears from the nuclear power business to research reactors, and also a bit on radioactive waste transportation. So let's go over there. So we just talked about radioactive materials and how we protect ourselves doing experiments on them. But radioactive materials are shipped around the country all the time on a routine basis. They're shipped to hospitals for use in medical procedures. There are waste products, low-level waste products that don't require a whole lot of shielding, that are shipped to places where they're safely stored for a long time. And so this technology developed at Argonne is our approach to ensuring the security and safety of those materials when they're being shipped. That's a concern of a lot of people, and what I'd like to do is explain to you how we handle that. So this is a typical storage drum for those materials for shipping and storage. It may have a little bit of shielding, but mostly it's a tight container, and it's got this ring around the top which is bolted shut, and this is the seal. And it turns out we developed this instrumentation package which contains a whole bunch of sensors. One of the sensors detects whether or not this seal is broken. So the concept is we'll put 1 or 50 of these on a truck, and these all communicate via wireless to a suitcase kind of device that has satellite telephone capabilities and monitors the conditions of these drums basically all the time. And it has GPS, so it knows where this box is. So it will know if one of these drums, let's say, falls off the truck. Not that that would happen, but if one of the drums is no longer there, it would phone home and say, hey, wait a minute, I'm missing drum number 47, and I'm right here at this spot, and it's been missing for 2 minutes. So this instrumentation package also detects water. It detects heat. So for example, if this truck catches fire and it gets hot, this phones home and says, I may have my boundaries challenged because of this fire, and I'm here at this point. It also detects shock. So if the truck has an accident, the shock from the collision will trigger this alarm, and it will phone home to the command center. The Department of Energy does use this technology when it ships its radioactive materials, low-level radioactive materials. So let's transition now to another kind of reactor that we haven't discussed at all today so far, research reactors. So research reactors are, in a way, the opposite of a commercial nuclear power plant. A commercial nuclear power plant uses the neutrons in the neutron chain reaction to produce heat, and it's the heat That's the economic value because it's used to produce power. In a research reactor, what we really want are the neutrons from the chain reaction. And to generate those neutrons, we have to produce heat. It's considered a byproduct, and it's not used to generate electricity. It's just disposed of as waste heat. So it's sort of the philosophical opposite. We use those neutrons to do experiments, make radioactive materials that are useful, and use them as radioisotope tracers in biological processes and other kinds of scientific experimentation. Now I showed you two power reactor elements, fuel bundles. One was for the commercial reactor. The other one was for our fast neutron reactor in Idaho. This is for the MIT research reactor. And you can see it doesn't have pins or rods like the others. This has plates. It's just a different geometry, and the chain reaction works essentially the same way. But the idea here is to have a lot of the neutrons leak out into the experiment parts of the reactor. In a commercial nuclear power plant, you want to keep all the neutrons in so that they can be used in the chain reaction and produce heat. So this is, it's still a reactor. It still produces thermal power, but not electricity. And the geometries are all very different from commercial nuclear power plants. So why are we interested in these at Argonne? Well, in the 1950s and 60s, the United States and other countries sold and gave away research reactors to countries and laboratories around the world and universities fueled with highly enriched uranium. Now, highly enriched uranium is a material which, if it falls into the wrong hands, could, at least in principle, be turned into a nuclear weapon. And after India set off its first nuclear weapons test in 1974, people in the United States and around the world started thinking, maybe that wasn't the best idea to fuel all these reactors with highly enriched uranium. It turns out that highly enriched uranium is very nice as a research reactor fuel from a technical point of view. There are lots of neutron availability. It's very relatively easy to design the reactors. But since 1978, Argonne, under the Department of Energy's NNSA, has a program for converting research reactors from using high enriched uranium fuel to low enriched uranium fuel. So to date, we have converted about 71 reactors. Another 25 have been shut down. There are about 250 in the world. So we've made a major dent in the risk of proliferation of these materials or diversion of these materials to nefarious uses. That kind of work is very interesting from a reactor engineering point of view because it involves material science and reactor design. It involves material science because we don't want to change these reactors. We just want to change the fuel elements. We want to keep all the same geometry, the same structure, all the same experiment facilities, and just convert the fuel. Well, that means we have to pack more uranium in the same volume, and that means we have to do a lot more material science. So there's a big material science component to it, as well as redesigning the reactor core itself. So I just showed you the fuel element from a research reactor. This is how they look in a reactor core. This is a little bit bigger than full scale, but you can see, just like a commercial power reactor, there's a rack of these fuel elements that are relatively tightly packed. And here in the inside, you can see a couple of experiment and irradiation locations where we can put other materials. Research reactors typically operate at much lower pressure than commercial power reactors, and that's important because the minute you have a very high pressure system, you make it very inconvenient to put these materials in and take them out again. So we like to operate at low pressure, and in many cases they operate at atmospheric pressure. So it's very easy to access these materials. So this is the MIT research reactor. Now I'd like to invite your attention to a research reactor in Jamaica, and there's an interesting story that goes with this reactor. First, let me describe the reactor. This is low power. It's 20 kilowatts. Remember, a standard full-size commercial nuclear power plant is 1,000 megawatts. So this has got a much lower power rating. These are the fuel rods. So not all research reactors use plates. Some use these rods and pins like this. This is a cutaway, so I've sliced off the front half and set it aside. And these are beryllium reflectors that go around the outside to keep the neutrons from leaking all the way out so we can use them in experiments. And in the beryllium reflector are these tubes called thimbles, and we can lower materials in those to be irradiated. So the neutrons leave the core and they bounce around in the beryllium reflector, and many of them eventually go into these thimbles and are absorbed by the materials in the thimbles, that's the purpose of this reactor. So this is, by the way, this is the full size. So the core is a little bit bigger than a paint can. So remember, the current commercial reactors we have are 12 feet across and 12 feet high. This is sort of like 8 inches on a side, way smaller. But you can do that because it's much lower power. So what is this reactor used for in Jamaica? Well, it's used for education and training for Jamaica and physics students and so forth. It's also used as an environmental tool. Jamaica, its main export, besides us going down there and drinking rum drinks on the beach and going to clubbing, is bauxite, which is aluminum ore. And bauxite, that's an important part of Jamaica's economy. Well, bauxite comes co-located with, sometimes with toxic heavy metals like mercury, cadmium, arsenic. And so these mining operations have some environmental effects. And this reactor was used to sample water from Jamaican rivers in order to understand the nature of their pollution. So samples of river water were put in this thimble here and irradiated with the reactor operating, neutrons flowing in, being absorbed in the materials in the water, including mercury, lead, cadmium, and so forth. And these samples, once they're irradiated, are taken out, and each of these radionuclides has like a fingerprint that gives you, it tells you what is in there and how much. So this is done at various locations, and you could go upriver and follow the path of these toxic materials, toxic heavy metals. Not all of them come from bauxite mining. There are these in nature too, because river beds have minerals along the bottom, and the water leaches these out. So the idea was to identify what water was unsafe to drink. And it's very important, because when children drink water contaminated with heavy metals, it's a very serious problem for developmental growth and intelligence and so forth. Think Flint, Michigan, for example. But also, they could follow upriver and find out which part of this was coming from mining operations, and then they could the Jamaican government could work with the mining companies to clean up their processes so they weren't discharging this stuff into the river. So this is a big success for Jamaica, and it's a good example of an application of a research reactor that people don't normally think of nuclear reactors doing. So we have one more stop here that will explain how we study accidents and how we understand the safety of our nuclear reactors. So let's go over there next. So this display is about how we know what we know about nuclear reactors. So when we design nuclear reactors, we use computer programs. We provide material data. We apply the basic physics of how these systems work. But how do we know that we're actually right, that we're actually on a computer computing what actually will happen, predicting what will actually happen under various conditions? Well, this is an example of how we do that. We run experiments that are similar to what happens in a reactor, and we analyze those experiments with the same computer software that we use to design reactors and analyze reactor behavior and so forth. So this is one of the best examples of that. This is called molten core concrete interaction. So the idea is if we have an accident like we had at 3 Mile Island or Fukushima, and the reactor fuel melts its way through the reactor vessel, which it certainly didn't at 3 Mile Island, but if it did, it lands on a big, thick concrete base mat underneath the reactor. And so the question is, does this fuel material keep melting through that and get into the environment, or does it ultimately stop before it gets out? And so we understand how materials interact with concrete, but we do these experiments to test those theoretical models that also has some experimental basis. And this is on a big scale, so this is basically full scale here. So we have this material, it's a mixture of uranium dioxide or uranium oxide, which is a nuclear reactor fuel material, and we mix it with thermite, which undergoes an exothermic reaction. In other words, the more it progresses, the hotter it gets, the more heat it releases and so forth. And so we'll ignite this stuff, and it melts down and sits on a concrete floor on a set of concrete that we want to understand. That concrete is instrumented. We have some additional heaters around the sides to make sure that the thing stays hot enough that we can get relevant information. And we then just let this proceed, taking measurements along the way, and we compare our predicted behavior of this material with what we actually see in the experiments. And then we know that our predictions are good predictions and they can be relied upon. And in fact, this particular set of experiments, which was internationally funded, has been used by regulators around the world, nuclear energy regulators, to help qualify the calculations of reactor designers that show that their reactors are safe. So thank you for joining me on this virtual tour. There is much more information available at the lab's website, www.anl.gov. And you can go to that website and actually arrange for a physical in-person tour once conditions are normal. And we bring in tour groups all the time. So thank you again. Bye-bye.